Good morning everyone. My name is Abhijit. Let's look at how to make a inverter and simulate it in electric. So before we could go further, let's make a library first. New library, demo underscore inverter. Okay. Let's make a new cell where our schematic will be. We can already see the library over here. Inverter. Okay. So we have our workspace ready. Go to components. This is where all the components are. Before we could go any further from here, let's look at the preference that I've already set. So technology, scale, select the 300 nanometer scale that we have, apply, and everything else I'm assuming you've already set it up. Let's go to tools, spice, check if everything is alright. Spice 3, third level spice simulator, click OK. So now all the setup is done, and let's look in the solutions I've already given you. That W by L for NMOS is 6.16, and that for PMOS is 13.31. So let's tick the PMOS and then NMOS. So before we could do anything else, let's first set the spice model. We need to set this spice model because when we give the simulator a specific library, this is the model that will read from the library and takes all the specification that the library has already set for that model while simulating it. So go to tools, simulation spice, set spice model. So we've selected the NMOS now. So there's a spice model that is there. So select the spice model text and click Control I. So there's a dialog box that opens up. So write NMOS, and you can leave with everything else as it is. NMOS, and anything else that you do over here will just position and vary how NMOS is written. Click OK. Just for readability, you can always drag it anywhere you want. Now let's do the same for PMOS. Tools, simulation, set spice model. Select it, Control I, PMOS. Okay, done. We're selected. We've done the spice modeling already. So let's select the widths. So when you say 2, so this is 2 into the scale. The scale is 0.3, so that means length is 0.6 micrometer, which is the minimum that we need to set, which is already set up over here. And I've set the levels for 49 for both of these, which is necessary. It is already mentioned here. Change to level 49 when using Edge Spice or Smart Spice. Okay, so this will be 13.31 into 2 because this is scale 26.62, and similarly this will be 6.16 into 2, 12.32. So they were done with making a PMOS and an NMOS. Let's make the connections. Click at which point you want to start the wire from. Left click on the point where you start from. Right click to the point where you want it to join. Similarly, okay. Now let's make connections for ground and VDD. Okay, we're done. So all we need to do now is make an input port and an output port. Input and output. So select the rightmost part of the input port with the left click, connect. Similarly, left click, connect. So we're done. So these are the different components of the circuit as you can see. Now there's a certain thing called export, so we need to name these ports for whatever names that we have to give them. Select any port and do control E. So we have an export dialog box that comes in. So export characteristics could be a lot of things. It could be like clocks, a lot of clocks, and then input, output, bidirectional. So we've selected the input port, so input be in. Click OK. So we can see that there is an input that has come in, and for output be out. That will be an output port. Okay. So this is an error actually, so it shouldn't be here. When you select the port, select the midpoint and click Control E, be in, change it to input, click OK. So that's all right. Let's try it once more. Yeah, now that is all right. So you select the leftmost part, and that is where input is from. And similarly for VDD, you select the center point. It's an input port. Click OK. Yeah, that is done. So since we write a spice model, and spice models take wire names also, so just to be sure we are done with that, change the wire names. Yeah, okay, we're done with the naming now. So yeah, save it once. So we're done with the circuit now. To simulate this, we need to write a spice model. I've already written the spice code, so let me just copy that. Here is the spice code, copy. So okay, so go to components, miscellaneous, there's a spice code. Click on the text, do Control I, select the multi-line text and copy your code. So as we can see here, so I've set the VDDs, and VIN is the input source name. I'm going to connect it to the VIN wire. Same goes with output. So output we have a 100 femtofarad capacitor, as we already discussed in the question. Click OK. So the spice code is ready. Save. So we're done with the inverter and the spice code now. So we have. I want to look at the pulse. Pulse is a 2 microsecond width pulse, so it's a full cycle of 2 microseconds, and I'm running a transient analysis of 4 microseconds, so that should be 2 cycles. And I'm selected the long channel model that is given, that is from the CMOS edu group. So yeah, we're done. So we'll select and simulate, go to simulate spice, write spice tech. So LTSPice is open because I already connected LTSPice with this. Select P out. So we've gotten the waveform now. So there are a couple of things that we need to make sure. Go to preferences, waveform. You can always change the width of the waveform. I prefer 3 or 4 because that is pretty easy to read. And next thing is, when you click on the name that is written over here, the waveform name, you get a cursor. I'll show you how to use it. And the next thing we should need to do is zoom into it. So we need the rise time and fall time. Let's look at the rise time first. Zoom into the rising edge. So yeah, so click on the name. We got a cursor over here, as you can see. Take it to 0.5 volts because that is the 10% of total. Right there. So you can see the value and the timestamp of that. So there you can click F4. You get a pointer over here, and the next point should be at 4.5. Sorry. Next point at 4.5 volts is right here. Click F4 at that point also. And once you close this dialog box, both the cursors will be gone. And just looking at the timing over here that is given as 224. So yeah, close that. This is the rise time that we have for this circuit. Yeah, so we're done with the rise time. Just zoom out. We have both the uh, cursors still there, and now let's go for the fall time. Yeah, take the cursor, put the first one at 4.5, second one at 0.5. So yeah, so the rise time, the fall time is already mentioned here. You can always take note of that. And F4, select the cursor, F4, select the cursor, F4. So you have both the pointers. Zoom out, you have all the pointers ready. If you want to move the pointers, you can just right click on the graph, edit, move, select one. This way there's better readability. We're done. You can always take a print screen, and we're done with that. So the next part is to calculate the power. So power can be calculated in different ways through the formula that is already there, but I prefer calculating power per cycle over here. So I'll be taking it as a product of VDD and the current that is flowing through that port itself. So let me simulate it again. VDD, here VDD, select, Control A, select both of them, click OK. It just take some time to come up. So yeah, we have that. Okay, so we have both the graphs, but the VDD seems to be hidden behind this. So we need a product of VDD and the I from the that port. So what we can do is select any of the graphs, right click on the name, and multiply it with the other graph, click OK, and it is plotted. Now remove the other graph. So we have the power graph that we say here, and just zoom in and point the markers. So these are just impulses, so you don't have to worry about the uh, width of these. So any pointer that you take, you can just add the power. It's almost the same power that we get from there. F4, you have the marker over there, zoom out, and then zoom in here. Okay, so we have to take this peak, take the marker, F4. There we got both the powers from there. And so yeah, zoom out, delete the cursors. You can always move the pointers, one there, done. So we have the powers also. You can add both these powers to represent the power that is taken in one cycle. So that comes to the end of this demo. Thank you.